Welcome back. We're still talking about confidence interval estimates for proportion, and now we want to look at sample size as it relates to this. So as a reminder, when we look at confidence interval estimates of proportion, we have this equation for error. So the error involved in your interval estimate, which is the difference between your point estimate and the max, or your point estimate and the minimum of your interval, is a critical value multiplied by the square root of p hat q hat divided by n. This is your error. So if we look at this equation, we see that we have a couple factors involved. We have error, we have your critical value, and then we have your sample size. Three main parts. Your critical value is really a function of your confidence level. So how confident are you? How close to your point estimate do you want to be? And how many samples do you want? When you're looking at taking samples, the number of samples you need to include is really, really important. Proportions come into play a lot when we're looking at elections. So if you look at a campaign and you look at any of the elections, they'll often tell you how a candidate is polling, and they'll give you a plus or minus. So they'll say, we have a certain candidate at 38 points plus or minus 7. So that plus or minus 7 means we've measured 38, that they have 38% of the vote, but our uncertainty, we can only guarantee with a 95% confidence that those values, if it's 38 plus or minus 7, are between 31% and 45%. So we end up with a range of values that our proportion could be. Now 7% isn't close enough. If that's too wide of a span, we might need to have a larger sample. So we need to ask ourselves, how close do we want to be? How confident do we want to be? And how much money do we have? Money directly relates to sample size. So if I take this error equation that we were just looking at, and I manipulate it, so I bring z over to the other side, I square both sides, I end up solving this for n. When I solve for n, I get this formula. N is equal to p hat q hat times z alpha over 2 over e, this quantity squared. So I've got this formula now. What I can do is I can use this formula to figure out roughly what sample size I need. That way, if I only need a sample size of 1,500, I don't need to spend money collecting 10,000 data points. Or if I need 10,000 data points, I'm not going to waste my time by getting a sample of 1,500 when that's not going to be good enough. But there's an issue in this calculation, and that issue is you must have an estimate for p hat. If we don't have an estimate for p hat, we can't use this particular formula. P hat shows up. And if this is my first time going out to collect data, I likely don't have an estimate for my sample proportion. So I can't use this particular formula. If you don't have an estimate for your p hat, we can use this formula. So if you have no initial estimate, we are going to assume p hat is equal to q hat is equal to 0.5. This is the worst case scenario. 0.5 times 0.5, let me pull out my calculator here. 0.5 times 0.5 is 0.25. If I take 0.6 times 0.4, it's 0.24, it's a smaller number. If I take 0.8 times 0.2, it's also a smaller number. 0.55 times 0.45, smaller than 0.25. 0.51 times 0.49, also a smaller number than 0.25. So 0.25 is the maximum number that this could be, or it's going to make our sample size that we need as big as possible. So it can accommodate any potential proportion that we might end up with. So this might be a case where if you have no previous information, I would go ahead and use this. So the first time I go out and collect data to find out how my particular candidate is doing, I might use 0.25. I'm going to assume that that's what the proportion is. But as I start to get values and I'm trying to refine them, I can input my previous estimate of p hat. So if the last information I knew was that my candidate had a p hat of 0.35, I can use 0.35 to figure out what my sample size should be for my next round of sampling. So let's look at how we might use these formulas for examples. A researcher wishes to estimate with 95% confidence the proportion of people who own a home computer. By the way, these examples are really out of date, so we're going to take them with a grain of salt, but they're very out of date. Kind of fun to look at. I think this is from 2007. So this is the state of the world in maybe 2007, maybe earlier than that. So a researcher wishes to estimate with 95% confidence the proportion of people who own a home computer. A previous study shows that 40% of those interviewed had a home computer. The researcher wishes to be accurate within 2% of the proportion. Find the minimum sample size necessary. Okay. So my two formulas that I have going, or I have two formulas. First, I want to pull information out before I have to make a decision about which formula to use. So my confidence level is 95%. That is going to correspond to a critical value of 1.96. So we know that confidence levels of 95% have a critical z-value of 1.96. Then I can go through and I can find, so this 40% is going to be an initial estimate of my p hat. So q hat I could get as 0.6, an initial estimate of my q hat based on previous information. I want to update that information. I think more than 40% of people own computers now. Accurate within 2% of the true proportion. So that within 2% of the true proportion, this is my error. So I need to consider that as my error. And I need to convert that into a decimal. So 2% is going to relate to 0.02. So this is a 2% margin of error, relates to 0.02 in terms of error. So I do have an initial estimate for p hat. So that means I can use this formula here. So my sample size should be equal to p hat q hat times my critical value divided by my error squared. So my values are, I'm going to plug those in. I have 0.4 times 0.6 times my critical value, which is 1.96, divided by the error of 0.02 squared. Okay, so 0.4 times 0.6 times 1.96 divided by 0.02 squared. N is equal to 2,304.96. You will always round up, so this means you need a sample. You need a minimum sample size of 2,305 to be 95% confident with an error less than 2%. In our next example here, we've got some slight differences. The same researcher wishes to estimate the proportion of executives who own a car phone. She wants to be 90% confident and be accurate within 5% of the true proportion. Find the minimum sample size necessary. In this case, I see that my confidence level is 90%. 90% relates to a critical value of 1.645. Within 5%, so that means my error is 0.05, but I have no initial proportion estimate. I don't have any information about how many people have car phones. There was no previous study on this. So I don't have this information. It's not available to me, so I need to use my other formula, which is n is equal to 0.25 times the critical value divided by the error squared. Okay, so 0.25 times 1.645 divided by 0.05 squared. 0.25 times 1.645 divided by 0.05. 270.6. So we need a minimum sample size of 271 to be 90% confident within 5% of the true proportion. What you can notice is if I were to repeat this same problem with a higher confidence level, my sample size is going to increase because as my confidence level gets higher, my z-score gets higher, which means this value, if this value gets bigger, this value gets bigger. As my error gets smaller, because I'm dividing by my error, as error gets smaller, my sample size gets bigger. And then my proportion is also going to come into play, but I have no control over my proportion. I can only control my confidence level, my error, and my sample size.